Hi everyone, this is Jayshree, a team member from Pixel Pioneers. We created a crop health monitoring model which is crucial for ensuring optimal agricultural productivity and addressing issues such as pest infestations, diseases, and nutrient deficiencies. Our project overview or aim is to develop a robust system for monitoring the crop health using machine learning techniques and remote sensing data. The system will analyze data collected from various sources such as satellite imagery, weather forecast, and ground-based sensors to provide the insights into the health status of the crops and detect any anomalies or issues that may affect crop yield. For this project, we have used a dataset sourced from Kaggle and is divided into three sets: training, testing, and validation. Here are the training, testing, and validation sets. In training set, it comprises of large portion of dataset and is used for training machine learning models. It consists of labeled data where each sample is associated with ground truth information about the health status of the crops. Features in the training set may include satellite imaging such as healthy, powdery, and rust data. In training set, we used to evaluate the performance of the trained models. It contains data that the model has not been exposed to during training. Similar to training set, it consists of features relevant to crop health monitoring but without the associated labels. At last, we used a validation set, which is used for fine tuning the model hyperparameters and assessing its generalization ability. It helps prevent overfitting by providing an additional set of data for model evaluation. Like testing set, it contains features without associated labels. We imported the OS model. In the dataset, particularly in training, we got 458 to 434 sets and test set as 50, validation set as 20. Here, the image path mentioned here defines the path to the image file that will be opened and displayed. Change this path to the location of the image you want to display. The with statement used here is to open the image file in binary read mode. Inside this block, the display image function is used to create an image object passing the image data read from the file f.read as mentioned here, which specifies a width of 500 pixels. This image object is then passed to display.display, the function which renders the image within the IPython environment. The target size. The whole model. These are the diseased leaf. Now we are going to talk about the model. The whole model comprises of convolution neural network using Keras API for image classification, likely for the task of plant disease detection given the context of the previous code snippets. Let's break. We used Keras model which imports sequential. This line imports the sequential class from Keras, which allows us to create a linear stack of layers for building the neural network model. From keras.layers, import The line describes or imports various layer types from Keras that will be used to construct the neural network. The Convo 2D layer is a layer creates a convolution layer with a specified number of filters and kernel size. Max pooling. We mostly use max pooling in convolution layer to perform the operation as max pooling to reduce the spatial dimensions of the input data. A flatten refers to the input data that into the 1D array which is required before passing it to the fully connected layers. The dense named represents a fully connected layer where each neuron in the layer is connected to every neuron in the previous layer. A model sequential initializes a sequential model which will be used to sequentially add layers. This model adds convolution 2D from with the shape of 225, 225, 3. The activation ReLU. Here we used a ReLU activation function which have a 2D convolution layer which adds a 2D convolution layer with 32 filters, each with a 3 into 3 kernel size. The input shape parameter specifies the shape of input data. Here the shape is 225, 225. As mentioned before, here we applied ReLU and softmax function. As I explained about max pooling of size 2, 2, flatten is used to convert the 2D output of the previous layer into 1D vector, preparing it for the fully connected network. The model dense is of 32 and softmax function. Finally, the softmax function adds another fully connected layer with 3 neurons corresponding to the number of classes, assuming a multi-class classification problem. The activation function used here is softmax, which outputs probabilities for each class. As this code defines a CNN model with a 2 convolution layer followed by max pooling layers for feature extraction, followed by fully connected layers for classification. The model is constructed using the sequential API in Keras. We trained a model with 42 epochs. Here we plotted our accuracy and validation set using a data visualization box plot. Here the blue line represents training, which sets to 85% to 90%, and the validation from 85 to 90%. As mentioned before, a project overview is to here the system will analyze data collected from various sources such as satellite imagery, weather stations, and ground-based sensors to provide the insights to health status of the crops. So we used a function with the data set collected from Kaggle, and the TensorFlow Keras is used with the labeled healthy, powdery, and rust. For the future enhancement, we are using weather forecast integration. Integrating weather forecast data into our crop health monitoring system is essential for understanding the dynamic influence of weather conditions on crop health. By analyzing parameters such as temperature, humidity, rainfall, and wind speed, we can anticipate potential risks to crops and optimize management practice accordingly. We are also using GPS location tracking, which is seamlessly integrate our system to enable precise geospatial mapping of crop fields. This technology allows farmers to monitor specific areas of interest and optimize resource allocation based on spatial variability in crop health indicators. By tracking changes in crop health over time, farmers can implement targeted interventions to address localized issues effectively. We created this project mainly based on the Zero Hunger Initiative. Our project is aligned with the Zero Hunger Initiative, which seeks to eradicate hunger, achieve food security, improve nutrition, and promote sustainable agriculture. By empowering farmers with actionable insights through our crop health monitoring system, we contribute to the goals of ending hunger, enhancing food security, and promoting sustainable agriculture practice. This initiative aims to uplift smallholder farmers and promote equability access to resource, ultimately fostering a more resilient and sustainable food system. Here we are all if our model predicted the leaf as healthy, then our farmers can improve their crops. If it predicts some diseases based on max pooling, we give some suggestions. We are also included the type of data set in the model which gives recommendations to the disease based on the type of disease. As a conclusion, our crop health monitoring system holds immense potential for revolutioning agriculture by providing farmers with the tools and knowledge needed to optimize crop production, mitigate risk, and promote food security. Through the integration of weather forecast data, GPS location tracking, and alignment with the Zero Hunger Initiative, we aim to make significant strides towards achieving sustainable agriculture and ensuring a hungry free future. Thank you.